All right, so what we're starting today then is we're starting to look at chapter 13. Chapter 13 is all about carbohydrates. And so, if you think about what this course is in terms of its structure, it's called General, Organic, and Biochemistry. We've done most of the general part. There's a couple of things left over still, but we've done most of the general part. We spent the last two chapters doing a good chunk of organic, recognizing functional groups, naming things, kind of going that direction. This is our first look into the biochemistry part. And so carbohydrates represent the first kind of biomolecule that we are going to look at. And they're the ones that we probably understand the most because these are sugars. And so in terms of just things that we know about sugars, we have at least some background in terms of what they are and what they are not. Now, what we'll see in this chapter is that we're going to get kind of a marriage of a lot of the things that we talked about individually in chapter 12, now coming up in chapter 13 together as we describe carbohydrate and carbohydrate properties. So let's talk about, well, what is a carbohydrate? So carbohydrates, which are sometimes referred to as saccharides, meaning sugars, we know them as a major source of energy for our diets. These are the things that make up sugars. These are the things that make up starches. These are the things that make up the kind of complex carbohydrates we find in certain plant materials, as well as in certain kinds of fruits and vegetables. At their core, carbohydrates are 3-element compounds: carbon, hydrogen, and oxygen. So unlike what we saw in kind of chapter 11 and even a little bit in chapter 12, we're not going to see fluorines, we're not going to see any kind of halogen atoms here. It's mostly going to be carbon, hydrogen, oxygen. In fact, it's going to be all carbon, hydrogen, and oxygen. But there are some things that we're going to have to tackle along the way that are going to be kind of tough for us to tackle, at least initially. In terms of types of carbohydrates, we can break up carbohydrates into categories based upon the number of sugar molecules that make up the overall compound. And so a monosaccharide, also known as a simple sugar, contains just one of these sugar compounds. Disaccharides, which we're kind of familiar with mostly in terms of sucrose, table sugar, these are 2 sugar compounds. And then there are the polysaccharides. The polysaccharides exist as kind of a long chain of monosaccharides. And in these, we get into things like cellulose, the stuff that makes up plant cell walls, the stuff that, gives kind of the rigid strength to a lot of plants. Now, in the case of these disaccharides and these polysaccharides, we need to understand that these are basically polymers. Now, if you're not familiar with what a polymer is basically just a long chain of repeating molecular units that make up a large compound. Right now, plastics have been in the news quite a bit just in general, But with what's going on in East Palestine, Ohio right now, they've become a lot more front and center because of vinyl chloride and what was released in that train derailment. Now, vinyl chloride is an example of what is called a monomer. Single molecule that, if you initiate it with the right kind of reaction, can react with other vinyl chlorides to create a long compound. We call that compound polyvinyl chloride, PVC. Lots of things are made out of PVC. Well, the same kind of reaction takes place with sugar molecules as well. The only difference is the reaction is a little bit different, but the idea is the same. Got a monosaccharide, I get it to react with another monosaccharide, they link together, and now I have a disaccharide. In the process of creating that disaccharide, that linkage that I had to make, it's going to cause me to drop off a water molecule along the way. If I wanted to take that disaccharide and make it longer, I can make another linkage and drop off a water molecule, and I have a trisaccharide. 3 sugars in a row. And if I did that many times, I'd end up with a polysaccharide. Now, unlike a lot of monomers, not unlike a lot of plastics, usually when plastics are formed, the reaction is kind of irreversible. Can't undo PVC to get it back to vinyl chloride, nor would I want to. But with disaccharides and polysaccharides, if I introduce hydrogen ions, so acid, along with enzymes and waters, I can break apart that linkage and get back the individual sugar molecules that started the whole thing. So let's take a look at monosaccharides because they kind of make up everything else that we're talking about. I can't have a disaccharide unless I put 2 monosaccharides together. I can't make a polysaccharide until I put together a lot of monosaccharides. The monosaccharides themselves fall into kind of these general parameters. Generally speaking, we are talking about something that has somewhere between 3 and 8 carbons in a chain. One of those carbons in the chain has to contain a carbonyl group. So we're talking about either a ketone or an aldehyde. So that's why we had to talk about ketones and aldehydes last chapter first, before we could even begin to discuss them here. Depending upon whether we have a ketone or an aldehyde, we can break up monosaccharides into 2 different groups. The ones that have aldehydes are known as aldoses. The ones that have the ketone group in them are known as ketoses. So within monosaccharides, I have the aldoses, which have an aldehyde at the end of the chain, and I have the ketoses, which have a ketone somewhere in the middle of the chain, usually close to the end. The other thing that makes sugar molecules is you're going to see that we have all these OH groups all over the chain. So every single carbon in the chain, other than the one that has the carbonyl on it, is going to have an OH group on it as well. And you can see this. So we've got erythrose here, which is an aldol, or excuse me, an aldose. And so we've got the aldehyde group here. We've got 3 other carbons, and each one of those carbons has an OH group on it. And here we have the ketone version of the same basic structure, 4 carbons again. And we'll see that we've got a OH group on the end and on the other end, and we've got an OH group on that middle carbon that's not the ketone. So we can classify monosaccharides based upon whether they have ketone groups or aldehyde groups on them. We can also classify them based upon the number of carbons. And so here's where our prefixes come up again. A triose would have 3 carbons in the chain. A tetrose would have 4. A pentose would have 5. A hexose would have 6. And then for 7 and 8, which are a lot more rare, heptose and octose would be. So again, we're using those kind of traditional numeric prefixes that we saw way back in chapter 6. And so now we can kind of put both of those classification systems together. Aldo plus hexose would mean a 6 carbon chain with an aldehyde on it. Keto pentose would mean we've got a 5 carbon chain because pento is 5. Keto would tell us that it's got a ketone on it. So we're basically just smashing together prefixes. So we can start to classify based upon those ideas, based upon those kind of smashing together of prefixes and suffixes. So in terms of some common, saccharides here, in these first 3, we have aldosaccharides. We've got aldehyde groups on each of them. The naming here, glyceraldehyde is the name of this one. It is an aldotriose. There are 3 carbons in the chain. Here we have a aldotetrose here because we've got 4 carbons in the chain. So this is known as threose. Here we have ribose, which is an aldopentose, 5 carbons in the chain. And then we've got fructose here, which is a 6 carbon chain, but it's a keto. So this is a ketohexose. Okay, so let's take a minute here and let's see if we can kind of wrap our heads around this first classification piece. We need to identify both of these saccharides, both as either aldo or keto, or, and as tetrose, pentose, or hexose. So take a minute here and see what you come up with on your own. And then we'll circle back and talk about it here in just a couple of minutes. All right, so in either case, our first task should be to identify the functional group. So in letter A here, I should be able to identify that this is an aldehyde group. And so that means that this is going to be aldo. And in letter B here, I should be able to identify that this is a ketone group. So that means that this is keto. Then it becomes a matter of counting the carbons. And here's where it can be a little bit tricky. It's very easy to forget the carbons on the ends because they don't look like they're built out the same way as everybody else. So I've got 1, 2, 3, 4, 5, 6. 6 is hex. So this would be an aldo hexose if we were classifying it both ways. In B, I've got 1, 2, 3, 4, and don't forget about this 5th carbon on the end. So 5 is pent. So we've got a keto pentose here. All right. So questions here in part 1. Well, so they have alcohol groups on them, but ketones and aldehydes are considered more important in terms of naming. Now, we're talking about carbohydrates here. Carbohydrates have these things in common. They will have one of these carbonyl groups, either an aldehyde or a ketone, and they will have those OH groups on every other carbon in the chain. And so what we're talking about here is, it's not an alcohol. There are some OH, there are some hydroxyl groups on there, but it's not an alcohol because we've got more substantial functional groups present. Carbonyl groups are considered more substantial. And so in those cases, when we have a carbonyl group there, we don't think about the OH groups as alcohol groups anymore. We think about them as hydroxyl groups instead. They kind of take on a lesser importance because of the presence of that higher functional group. All right, other questions and thoughts here? Okay. So section 2 here concerns a phenomenon known as chirality. And so the word here is chiral molecules, not chiral. Now, chirality is a fancy way of saying that you have two images that are mirror images of each other, but not superimposable on top of each other. So what we mean by that is if you hold your two hands up, you'll notice that they are mirror images of each other. Thumbs on the inside, pointer, middle, ring, pinky. They are mirror images. But if I try to lay my left hand on top of my right, or my right on top of my left, they don't fit over top of each other. Now, yes, I could do it this way, where I have a mirror image in between my palms, but even at that, I'm not actually superimposing the same thing on each side. One side is the back of my hand, and the other side is the front of my hand. So they're not really mirror images of each other. They're mirror shapes, but not truly mirror images. when this phenomenon occurs in chemical compounds, we call it chirality. And where we see chirality is, well, I love when definitions tell us and use the word that is being defined as part of the definition. So for a molecule to be considered chiral, it has to have what is called a chiral carbon atom. Chiral carbon atoms basically are just atoms that have 4 unique groups on them. And so just as an illustration here, I brought out my modeling kit today, just in case you had any reservations about whether or not I wasn't cool. But it's really hard to see this without actually seeing it in not a picture. So I'm going to pass these around. Just ignore, let's assume that both of the middles here are carbons. I only have one black ball. But if I were to look at these 2 compounds are mirror images of each other. I can draw a plane right between the 2 of them. And I would have the beige ball in the front, the dark green in the back, the white on the side, and the light green on the top. But I get the same problem that I have with my hands. I can't lay these on top of each other and get the same orientation. 2 of the groups are going to be out of place. So they are mirror images, but I can't just lay one on top of the other and get the same molecule. This is different from let's say that I have a molecule like this, where I can definitely get the same mirror imaging, but I can also superimpose them, because all I need to do is rotate this one, and they will be identical in every way. So chirality is not just a matter of, can I rotate it or not? It's really a matter of, because I have 4 different things, and because carbon molecules are 3-dimensional and not 2-dimensional, I end up not being able to superimpose them on each other. And where this property really kind of shows up is primarily we talk about it in terms of light. The ability to, one of these atoms in one direction will cause light to spin this way, and one of these will cause light to spin the opposite way. So they really do have differences, not just in terms of appearance, but also in terms of how they react physically to certain kinds of stimuli. So I'm going to pass those around just so you can kind of, it helps, because we're going to show things here in 2 dimensions, and it's going to seem real kind of, okay, yeah, but I don't get it. But if you can hold them in your hand and show yourself that they are actually different from one another, in spite of the fact that they are the same as each other, it should help with this idea. Chirality is a really hard thing to get your head around. So here's a more chemical example. Let's say that I have a carbon that is bonded to hydrogen, bromine, chlorine, and iodine all on the same carbon. Well, the position, how I look at that molecule in creating these mirror images, it appears the same. But like I showed you before, when I try to overlay them on top of each other, I'm going to end up with two balls out of place. So in this case, it's the chlorine and the bromine that are permanently out of position to each other. When this happens, we call the molecules themselves enantiomers. So enantiomers are stereoisomers. So we've talked about different kinds of isomerism thus far. We've talked about the idea of structural isomerism. Same compound, we just move a methyl group here, move a methyl group there, and we get a different arrangement of the molecule. Now we're talking about stereoisomerism, where even the arrangement appears to be the same in terms of I've got a carbon that is bonded to these four things, but the exact position of those four things matters. Because one's going to cause light to go this way, and another one's going to cause it to go the opposite direction. When we have stereoisomerism, the molecules are called enantiomers. And so one of the things that we are going to want to be able to do in this section is really get a handle on how do I identify when I have a chiral carbon. And remember, the definition of a chiral carbon is I'm looking for a carbon that is bonded to four different things. And if it's bonded to four different things, then I have a chiral carbon, and then I also have a chiral compound, because a chiral compound would contain that chiral carbon. So if I look at this, let's start with B. I'm looking at this carbon here in the middle. I can see that it's bonded to chlorine, it's bonded to a methyl group, and it's bonded to two hydrogens. Since those two hydrogens are not different from each other, this carbon is not chiral. And if it's not chiral, we call it achiral. A just being that prefix that means not. But if I look at these other ones, this carbon here, it's bonded to a chlorine, it's bonded to a methyl, it's bonded to a bromo, and it's bonded to a hydrogen. All four of those are different things. That carbon is chiral, which makes that molecule that it's in also chiral. With letter A can be a little bit trickier than it seems. Because if on first glance, you look at this and say, okay, I've got a chlorine group, I've got a carbon group, I've got another carbon group, and I've got hydrogen. This is achiral. That carbon is bonded to two other carbon groups. Not actually the way we want to look at it. The way we want to look at it is we need to consider the whole thing that is attached to that carbon, not just the atom that it's bonded to. So I look at this and say, okay, this is a methyl group, and this is an ethyl group. Methyl and ethyl are two different subgroups. They're different things. and the hydrogen is also different. So I've got 4 different things here. This is chiral. So when we're looking for chirality, we have to explore what is bonded to an individual carbon, and is there variety in terms of all 4 of the bonds that the carbon makes. So we will never see chirality on carbons that have multiple bonds. So if I have a carbon that's in an alkene or an alkyne, where it's making a double bond with carbon or a triple bond with carbon, that's not going to be a chiral carbon. It can't be. Same thing if it's in a carbonyl. If I'm looking at an aldehyde or a ketone carbon, those aren't going to be chiral either. They can't be. Similarly, carbons that are just part of normal chains aren't going to be chiral either. It's just part of a linear chain, a CH2, a CH3. They aren't going to be chiral because we've got multiplicity in those hydrogens. That carbon's bonded to 2 other hydrogens. It can't be chiral because 2 of the positions are exactly the same. So chirality really is in the recognition here of finding carbons that are unique, that have unique bonding capabilities to a variety of different subgroups. Now let's take it a step further. I think we can all assert that A and B both consist of mirror image molecules. If I put a mirror plane right in the middle here, I would be able to match up on either side the different pieces and parts of the molecule. So I've got CH3s toward the plane. I've got CH2OHs up top. I've got bromines on the bottom. I've got hydrogens on the outside. How do I know if they are enantiomers? Chirality. If the carbon is chiral, then they are enantiomers. If the carbon is not chiral, then they can be superimposed on each other. Think about the example I did with the molecules. If I have 2 white balls on there, I could just rotate one to get the other. So we can see that this carbon here is chiral. It's got a hydrogen group. It's got this methyl alcohol group. It's got this methyl group here. It's got a bromo group there. All 4 are different. These are enantiomers. These, on the other hand, we can clearly see that these are achiral. And so the way to prove it to ourselves is if we did a 90-degree rotation of this molecule, we would have, wrong direction. If we did a 180-degree turn of this, about this axis, we would get the exact same molecule. And the reason for that is the lack of chirality. So again, just as an illustration. Letter A is like the example I passed around to. Letter B would be like this molecule. Where I can show that mirror image thing again. So I've got it here. But if I rotate this 180 degrees, now I can superimpose them. So I'll send these around to you again. That's the difference between chiral and achiral. In the chiral molecule, you can spin that one molecule as much as you want. You'll never be able to overlay. But if it's achiral, like in B, all you need to do is rotate one of them, and they'll fit right on top of each other. All right, so the next thing that we want to get into is we want to try to start to figure out some ways that we can try to model this three-dimensionality without actually having to draw something three-dimensional. And so this is where what are called Fischer projections come in. Fischer projections are molecules that are going to utilize kind of a vertical structure for the chain. So I'm going to show that carbon chain in this vertical line now. And the assumption is, and again, you can hold these molecules and kind of see it for yourself. If you're looking square in the face of one of those middle atoms, you'll notice that two of the atoms are going to point away from you, and two are going to point toward you. What a Fischer projection does is it puts it out there and defines which ones are pointing towards you and which ones are pointing away. Now we can show that with wedges and dashes. Wedges indicate things coming in your direction. Dashes indicate things that are coming away from you. But what a Fischer projection basically does instead is it says, okay, I've got this vertical chain. All of the vertical bonds are going down. All the horizontal bonds are going up. So vertical means down, horizontal means up. And the other thing that these Fischer projections will show is they will show chirality. Because any place where we have an intersection of lines, that is going to indicate a chiral carbon. So we don't have to go through quite as much heartburn about figuring out what is chiral and what is not. If I have a Fischer projection, The things that are chiral are just going to be shown as these series of vertical crosses. The things that are achiral, we're going to continue to show in this kind of expanded structural formula. Now, with Fischer projections, we have some more nuance to introduce. There are ways to subclassify these different isomers. And the words that we use, or excuse me, rather the letters, are D and L. Now, the DL notation is actually really easy. We're looking for a hydroxyl group, an OH. And if the OH group is on the left, then we call it L. If the OH group is on the right, we call it D. Question is, which OH group do we look at? And the answer is always the same. We look at the OH group on the last chiral carbon coming down from the carbonyl. So if I've got a long chain, carbonyl group's always at the top, I just follow it down to that last chiral carbon, and I look at where's the hydroxyl group. If it's on the left, it's L. If it's on the right, it's D. The naming of the rest of the saccharide has a lot more to do with where those OHs and H's are in the other carbons and how many carbons are in the chain in total, and whether it's an aldo or a keto sugar. But in terms of D and L assignments are pretty easy. We're looking at that last chiral carbon. Is it on the left, L, or is it on the right, D? All right, so we have two aldoses here. And to be even more specific, we have two hexoses, because we can count 1, 2, 3, 4, 5, 6 carbons in the chain. So we've got two hexoses. Question is, which one is D and which one is L? And remember, to figure it out, we start at the carbonyl. So in this case, it would be at the very top. If this was a ketose, then we would just start at that next carbon down. And we draw down to, okay, here's my last chiral carbon. The OH group is on the right. So this is the D-isomer. For letter B, I do the same thing. The last chiral carbon is the last place where it crosses. The group is here on the left. Left is L, so this is the L-isomer instead. All right, any questions so far? Okay, so some places where this is actually kind of useful and important. Enantiomers. Why do we care about this chirality? Well, because a lot of times physical and chemical properties are going to be affected by the orientation of those molecules to each other. So take, for example, the DOPA. DOPA is used in one of the drugs that treats Parkinson's. And it has two enantiomers. It has the L-DOPA, which is the one there on the left, and it has the D-DOPA, which is there on the right. Now, the two compounds, you can see, they are enantiomers of each other. The chiral carbon is this one that is given by the star. Here's the thing. D-DOPA doesn't work in your brain. Your brain can't process D-DOPA to create the dopamine necessary for raising your serotonin levels. So as a Parkinson's drug, D-DOPA doesn't work, ineffective. But L-DOPA works really, really well. Why the difference? Well, it probably has a lot to do with enzyme action. With enzymes, we usually have to think about kind of like a lock and key idea. So the active site where the DOPA drug is going to come in has a very particular key necessary. This arrangement on the L side fits into the lock. The lock turns, the key turns the lock, it works. That arrangement on the right, the D-DOPA, it doesn't. The arrangement of the molecules is wrong. And as we said, since the images are non-superimposable, I can't just rotate that molecule to get it to work. It won't work. All right, in section 3, we're starting to look at the Fischer projections of monosaccharides. And we're going to focus primarily on the D-isomers because they're the more common ones. The L ones do exist, but the D ones are far more common. So we're going to kind of slant our focus more toward that D side. Now, there are 3 monosaccharides that you need to become very familiar with out of this kind of chapter. They are glucose. Glucose, we can look at, it's a 6-carbon aldose. So it's an aldohexose. And what sets it apart as different, obviously we have the D hydroxyl group on the right-hand side, but it's the fact that it only has the one hydroxyl group on the left side in that 3rd position. That's what makes glucose glucose. If I compare that to galactose, we'll see that the 6-carbon structure, very, very similar. Everything looks kind of the same, except for in this 4th carbon position, it's different. So the difference between glucose and galactose is that 4th carbon. How that 4th carbon is basically turned 180 degrees. And then in fructose, we also have a hexose, 6-carbon chain, but this is a keto hexose. So a little bit different. What we'll see is that, structurally speaking, it looks really similar to glucose. The only hydroxyl group on the left-hand side is in that 3rd position. But the difference between them is the difference between a ketose and an aldose. So I'm not going to lie to you. These nuances are going to be kind of cumbersome and easy to confuse. The only thing that we can kind of hope and bank on is that as we do more of them, we can kind of start to recognize the differences between them and not trip over our own feet quite as often as we look at more and more examples. So most of what we talk about are the 6 carbon values. There are 5 carbon monosaccharides. Ribose is probably the most common of those. And we can see really the non-superimposable kind of shape here. We're really just talking about what that carbon looks like. And you can see that on the L side, what does that do? It turns all of them to the left-hand side, and the D turns all of them to the right-hand side. And you can see the same thing for L and D glucose. Switching the position of that bottom carbon also turns all of the other carbons the same way. Now, where do we see some of these? Glucose. Glucose is probably the most common simple sugar that we know. We find it in fruit. We find it in corn syrup. We find it in honey. It has a very kind of sweet, pleasant flavor. It is an aldohexose. Formula for it, C6H12O6. In the body, we refer to it more as blood sugar or as dextrose. The other thing that's important to know about glucose, it's a building block. We find it in a lot of other sugar products. So we find it in some of the more common disaccharides, like sucrose, like lactose, like maltose. We also find it in a lot of the polysaccharides, like glycogen, like cellulose. D-fructose, another very common simple sugar. We can derive it from sucrose, so table sugar. If we break down table sugar into its individual sugar components, one of those would be D-glucose, the other one would be D-fructose. It is a ketohexose. So instead of an aldo, it's a keto. Has the same formula, C6H12O6. Of all of the carbohydrates, it has the sweetest taste. In fact, it is twice as sweet in its taste than table sugar, which makes it a really good sweetening agent. This is basically why high fructose corn syrup exists as a thing. We take fructose and water, we boil off as much of the water as we can, and we're left with this very sticky syrup that is incredibly sweet, that can be used as a very common sweetener for things that need to be really sweet. So in honey, we have both glucose and fructose. They both exist kind of independently of each other, even though we know that when they do go together, they make sucrose. In most honey, they stay separated. Galactose, which we mentioned before, also an aldohexose, not something that we find naturally, but one that we can obtain through one of those kind of breaking it down reaction. So if we take lactose and break it apart into its pieces, we would end up with galactose and glucose again. Structurally, we mentioned this already. Very similar to glucose. The only difference is the positioning at carbon 4 is flipped around. The OH group and the H group are on the wrong side. All right, the last thing that we're going to mention today, and we're going to come back to this on Thursday, Fischer projections kind of give us a lot to think about. The problem with Fischer projections is that oftentimes they don't actually represent how the sugar actually looks. Most of the time, saccharides will form ring structures. And that'll be kind of the most stable form that they make. So when we're looking at pentose and hexose sugars, which make up most of the sugars that we encounter, instead of staying in a 6-carbon or a 5-carbon chain, they end up ringing around each other. And what's even more weird about these ring structures that they make is that these ring structures come as a result of a chemical reaction with themselves. So one part of the molecule literally attacks another part of the molecule and creates a ring in the process. Now, these ring structures are known as Hayworth structures or Hayworth projections. And we'll get into how we get to that in greater detail on Thursday. But basically what we do is we can convert one of these structures from a Fischer projection. So let's take a look at one example. So let's look at glucose here. Three, 4, 5, 6. So if you're asked to draw a Hayworth project or Fischer projection, basically what you do is you draw the end group, whether it's an aldehyde or an alcohol group. You draw a line to the other end of the tail, and then you just draw a series of crosses to represent the carbons in between. So this is how we get 6 carbons overall. For D-glucose, it would be just the 1 OH on the left side in that 3rd position. And then what we're going to do is we're going to rotate this by 90 degrees. So it's going to be more closely resembling what we would see if we were to draw this kind of linearly. I'm actually going to rotate it the other direction. So we've got CH2OH here. And then on the other side, we've got the aldehyde group. And here's carbon 2, 3, 4, 5, and 6. How do I get the ring? Well, like I said, it ends up attacking itself. So what's going to happen is that this OH group from that last chiral carbon, the one that determines whether it's D or L, is going to come over and bond to the carbonyl carbon here. And in the process, this hydrogen is going to move from here over to here to make an OH. And so what we end up with at the end here is we're going to have a ring structure like this, where this CH2OH, this is still that end. So this was carbon 6. It's still carbon 6. This is carbon 1, 2, 3, 4, and 5. So, this used to be the aldehyde group. And now it just looks like an alcohol group. Looks like a normal OH because the OH off of this 5th carbon went and created basically a bridge, a 5th member, or excuse me, rather a 6th member to this ring. And so what we will get into on Thursday is in kind of the recognition of how this goes about happening and how to recognize what are known as alpha and beta forms of these sugar rings. And once again, alpha and beta have everything to do with the position of this OH. This case, instead of left or right, we're going to talk about up or down. So that's all I've got for today. So Thursday, we will pick up the rest of this and we'll start to talk about kind of some more things that we can do, as well as getting into what happens when these guys link up with each other. Have a good day.